Hello and welcome to Statistics Day 1. I've got a warm-up based off of Day 0, which was last class's video. If you haven't watched that video yet, stop this video right now and go over to Statistics Day 0 because you won't be able to do tonight's homework if you don't watch that video. So, watch that video first. If you have watched it, pause this video and get your calculator out and try this. See if you remember what to do. Go for it. Okay, let's give it a shot. It says Mr. Koziel has 17 students in his high school golf club. Each student played one round of golf. The summarized scores of his students are in the table here. Find the following values for this set of data. Okay, so when you got a frequency table like this, you have to put the stuff in the left in L1 and the stuff in the right in L2. Okay, so if I go to, remember you go to Stat and then Edit, you want to clear out everything that's in both of these if you have stuff in it and plug these in. So I got 70, 73, 75, 80, 85, 86, 90, 92. And the corresponding frequencies are 4, 3, 2, 3, 1, 1, 2, 1. Okay, those are all in there. After that, you go to Stat, Calc, one variable stats, never two variable stats, always one variable stats in this class. Since we do have a frequency table, we want L1 here and L2 there. Remember, if L2 isn't listed, go second 2. That's how you get L2. If you only had a list of data, you would not want to put L2 in there. I think on tonight's homework, it's just a whole list of data, so you put it all into L1 and you clear this out so that there's nothing there. But since we do have a frequency chart there, we want to put L2 there before we calculate, and we get all those values. Now, a lot of these you can get from the calculator screen. Set everything to the nearest hundredth if we needed to. So the mean, that's the first thing, x bar is 78.35. So 78.35. All right, and then if you arrow down, you see a lot of this other stuff. There's median 75. It's the middle number. Now notice mode isn't on here, but remember mode means most often. So in a frequency chart, that's easy to find. What's the score that happened most often? 70, because it happened 4 times. So the mode is 70. And again, modes can have more than one value. So if there was another thing, like let's say this was 4 instead of 3, you could just say 70 and 80. Quartiles 1 and 3 you can get on here. Quartile 1 is 71.5 and 3 is 85.5. So that means 25% of the scores are at or below 71.5 and 75% of the scores are at or below, what did I say? 85.5. Do the right quartile one? Did I forget? Yep, 71.5. Okay. Interquartile range, that's nothing that's not on your calculator, but think of what it sounds like. The inner quartiles, the distance between them. So how big is that range? So quartile 3 minus quartile 1, if you subtract these two, 85.5 minus 71.5 is just 14. So that has a span of 14. Standard deviation is on here. That's that lowercase sigma, that O of x, 7.50. Oops. And the variance, again, that's not on here, but that's standard deviation squared. And when you find that, you shouldn't round it, but it's hard for me on the computer to copy that all down and look at it at the same time. So 7.498558. That's all I got, but take all of it and square it. So 7.498558 squared. The nearest hundredth, it'll still be accurate, 56.22. Okay, so just remember variance is standard deviation squared. Okay, now there's one question hidden down here that you probably didn't get a chance to try. How many students' scores would fall within one standard deviation of the mean? So again, within one standard deviation, something we're going to be talking about a lot more today. So I want to look at how many score one standard deviation below the mean and how many score one standard deviation above the mean. Before I do that, I have to find what those scores are. So the mean was 78.35. If I subtract 56.22, that'll give me one standard deviation below. If I do 78.35 and add 56.22, that'll give me one standard deviation above. So 78.35 minus 56.22 is 22.13. What am I doing? Sorry, just kidding. Hope you all saw this. I was using the variance there. It needs to be standard deviation. I knew that was too big. It should be minus 7.50 and plus 7.50. Sorry, get over it. So 78.35 minus 7.50. That sounds better. 70.85 and 78.35 plus 7.50. It's 85.85. So 70.85 to 85.85. You know, that's within one standard deviation. So if you think of this like a number line, I want to know how many scores fall between 75.85 and 85.85. So if I were to list out everyone's scores on a number line, how many would fall within here? Well, this is outside, it'd be over here. This is outside, it'd be over here. 86 would be just outside, even though it rounds. But 85 would be in here, 80, 75, 73. 70, again, is just outside over here, so that doesn't count up here. So these are all the scores that fall between. Now it wants to know how many students. Remember, there's 3 of these, 2 of these, 3 of these, 1 of these. So add up the frequencies. 2 plus 3, 2 plus, 3 plus 2 plus 3 plus 1. 3 plus 2 plus 3 plus 1. And the answer is 9 scores. Here's your random fact. Mario from Super Mario was originally called Jumpman. Mario's a better name. Okay, good? Okay, let's go over to today's notes then. Now, at some point, I'm going to refer to this chart. So hopefully you have this reference table, this normal distribution based on standard deviation. I'll explain what this all is a little bit later in the lesson. But the next few days, we're going to deal with something called the normal distribution. Okay, so the normal distribution. Before I can tell you which graph models the normal distribution, I need to tell you a little bit about it. A normal distribution, if a graph is normally distributed, then here's some characteristics of it. Sometimes they say it's mound shape. Or sometimes they call it a bell shape. We talked a little bit about that in the last video. They say it's symmetric about the mean. So the mean would be right in the center of the curve, or at least in the center of where all the data is. And the 3 big things that represent data, median, the middlemost value, should be about equal to the average value. That should also be equal to the mode, so that should occur most often. So if all of those things are true, then you've got a graph that's normally distributed. So based off of that, which one would you say is bell-shaped? Which one's symmetric about the mean? And where's the median, the middlemost value, the most value, should all be at the same value. And that's this one over here. So that's a normal distribution. The mean, median, mode would all be right at around 50 there in the middle. It's bell-shaped. By middle, again, I mean middle of the data. So here, the mode is here. The median might be off here a little bit. The average might be a little bit further out even. They're not all at the same spot. We would say this is skewed which way, left or right? This is skewed right. Even though most of the data is on the left, it's got some right values that are skewing the results, some high values. So this would be not normal. Okay, let's look at some others down here. Identify the shape of each distribution. Okay, so is it normal or not normal? Which ones are normal? I would say this is normal. It's pretty much like a bell shape since it's all symmetric. I would say this one's normal. And I would say this one's normal. It has to have all those characteristics that I talked about earlier. This first one is not normal, even though it's kind of symmetric. So we'd call this maybe a uniform distribution. And that really just means that it's spread out equally everywhere. It is symmetric. It's just not bell-shaped, so it can't be a normal curve. The ones that are normal because they're bell-shaped, and they're also symmetric. So we could say that with all these. This is also bell-shaped and symmetric. Even this one, even though it's spread way out, kind of down on the graph, it's still bell-shaped and symmetric. And then this top one up here, this one's not normal at all. What is it? Is it skewed? It's skewed which way? Yeah, this one's also skewed right because there's some right-hand values up here that are pulling the values, and we'd say it's not symmetric or asymmetric. Okay, so the only types of distributions I'm talking about right now are the normal distributions. And when I say distribution, I'm talking about how the data is distributed. So all of these curves that you see represent data. And maybe if you see the next page with a specific example, it'll kind of make more sense what you're looking at. Histogram below shows the distribution of heights of 1,000 young women. So it's kind of a histogram. So the mean of the distribution of women's heights is 64.64 inches, and the standard deviation is 2.75 inches. Interpret each of these within the context of the problem. Okay, well, when you hear the word mean, so if the mean is 64.64, what word should you think of when you hear mean? Average. It's the average height of the 1,000 women. And you can even think of this as like a typical height if it's a normal distribution. It's not super tall, it's not super short, it's just typical height. So 64.64, the average is right about here. A standard deviation we spent some time talking about in the last video, but if the standard deviation is 2.75, what that actually means is it's the typical number of inches that a woman's height is from the mean. Typical number of inches a woman's height is away from the mean. Now, what's that mean? So that means if I want to find what those heights are, what I just did in the warm-up, if I do one standard deviation above and one standard deviation below, I would take 64.64 minus 2.75. And I would do 64.64 plus 2.75. And I can do that on my calculator. Wish there was a plus or minus button on here. 64.64 minus 2.75 is a height of 61.89. And 64.64 plus 2.75, oops, is 67.39. So 61.89 and 67.39. Now, when I say it's the typical number of inches a woman's height is away from the mean, that just tells you that most women fall between these heights. So 61 would be somewhere over here-ish, and 67 would be somewhere over here-ish. So if it's saying that most women are somewhere in this range in here when I'm coloring blue. So these women over here might be considered tall, these might be considered short, but the ones in the middle are like the typical height, average height kind of. And that's what a standard deviation is. It's telling you how spread out it is, where most of the data falls. Let's be a little more specific. What proportion of the data fall within this range? Let's look at the graph. So histograms are frequency charts. They're telling you how many people fall within here. And it's giving you a frequency in terms of percents. So it says take the sum of the bars in the histogram within this range. So between that 61.89 and 67.39, if I add up all these bars, we've got like 10% of women here, 12% here, 14% are here, 13%, 11%, maybe this is 10.5%. If I add all those up, I get 0.705, which means within one standard deviation, we've got about 70.5% of all people fall within there. So it makes sense that about within one standard deviation, 70% of the people have an average height, normal height. It says now refer to your normal curve based on standard deviation chart and add up the percentages that are one standard deviation above and one standard deviation below. This is what I'm going to pull out this chart. So grab this page for a second. This is kind of a theoretical chart. If the average was 0, so the middle is always x bar, so that's the average, and all of these things over here represent number of standard deviations away from the mean. Number of standard deviations away from mean. So if I wanted to know where one standard deviation below was, that's this spot right here. This is x bar minus 1 standard deviation. And similarly, this is x bar plus 1 standard deviation. So if I want to look between here and here, it's kind of like what I just did with my specific example with the women's heights over here. And I added up the percentages that fell in these range. Well, that's what this does. Here I've got 15.0, 19.1, 19.1, and 15.0. So if I add all of those up, let's see what we get. So 15.1, these are all percentages, plus 19.1, plus 19.1, plus 15.0. Comes out to be 68.2%, which is pretty close to what this distribution told us. Are these sums close? Are they close enough to assume our distribution is normal? We'd say they're close. We've got 68.2% versus 70.5%. Now 68.2 is the ideal, and the idea is this is 1,000 women. If you took 1,000,000 women, it would kind of normalize out and be even smoother and look more like that theoretical curve that I showed you. So this is close enough. To assume entire population would be normally distributed. and this is going to be a theme that kind of comes throughout the statistics unit. Close enough. Is it close enough? It's kind of a vague term. But if I wanted the heights of every woman in the world, that'd be almost impossible to collect that data. You probably couldn't collect that data. That's why we have to take smaller samples. And if the smaller samples look normal, the theory is if I were to look at the entire population, it would be perfectly normal. Okay, it's kind of theory, a little math hand waving. Okay, so the other thing I need to talk about today is z-scores. When a distribution is normal, we can use z-scores to standardize it to any set of data. A z-score is really the number of standard deviations away from the mean. Any normally distributed data will yield a z-score. So if your data is normally distributed, you can match it up to this chart by using these z-score things. Like that number, what was it? In the last example, this 67.39 number that was one standard deviation above, I could use a z-score, this formula I'm about to show you, to get 1, so that I know where to look at on the chart. Basically, you're solving for the standard deviation part of it. Okay, so a z-score is equal to the observed data minus the mean divided by the standard deviation. Positive z-score just means that the data you're observing falls above the mean, which shouldn't be too crazy because if this is bigger than the mean, this is going to turn out to be positive. Similarly, negative is just going to mean that the data falls below the mean. Okay, so femur length, it's a bone, is normally distributed. The mean is 17.5 inches with a standard deviation of 1.3 inches. Calculate the z-score of the following femur lengths, round to the nearest hundredth. So as soon as you see normally distributed in a problem, you should immediately think, okay, I'm thinking bell curve. And furthermore, I know that the mean is 17.5, so that would represent 17.5 because that's right in the middle of a bell curve. So if I wanted to find all of these z-scores, I'm using this formula. A z-score of 18 inches, the observed data is 18 inches, minus the mean of 17.5, divided by the standard deviation, which they tell us is 1.3. Remember, that's standard deviation. And if I do that, I'll use alpha y equals for it. What's that? Try this again. If I do, oh, you know what? I'm in classic mode. That's why it's not giving me a nice fraction. Try that. So if I do 18 minus 17.5 divided by the standard deviation of 1.3, we end up with 0.38. Okay, so all that's telling us is that if I look at this chart, 0.38 would be right about here. I'm just a little bit above the mean. I'm in this 19.1 section here. 15 inches, you'd take 15 minus the mean divided by the standard deviation. (15 minus 17.5 divided by 1.3 gets you negative 0.192. So now I'm more than one standard deviation below. I'm almost 2 standard deviations below the mean. So if I was looking at my bell curve, negative 1.92, there's negative 1, there's negative 2, I'd be over in this section somewhere. So not many values are that small. 17.4 inches, well, that's really close to the mean, so I'd expect that to be in the middle, but a little bit below. So I'm going to get a negative z-score out. So the top is just going to be, I can kind of do that in my head, it's going to be negative 0.1 divided by 1.3 has a z-score of negative 0.08. So that tells you you're almost in the center. 17.4 inches would be a pretty typical value to get. What's 17.5 inches going to give you? Yeah, that is the mean. So if you are observing the mean, and I plug that into the formula, you're obviously going to get 0. So 0 is where the mean is, 0 standard deviations away. This one is similar to 17.4, but now I'm 1 standard deviation above the mean. So it'll be positive 0.8, or 0.08. Then finally, if you tried 20 inches, that's pretty high above the mean, 17.5 over 1.3. Does that come out to be 20 minus 17.5 divided by 1.3, positive 1.92. So we were that far below the mean in part B, now I'm that far above it in part F. Okay, so that's how you find z-scores. Then it says, what seems more likely, the length of 20 inches or the length of 17.4 inches? Explain. Well, 20 inches we just got had a z-score of 1.92. And 17.4, which we found over here, had a z-score of negative 0.08. So which one would be more likely? Again, it's all about where it falls. So 1.92 falls all the way up here, not very likely. Only 4.4% of the data have one that high. But negative 0.08 is right around here, way more data values. Think of this as a histogram. 19.1% of the data is right there. So which one's more likely? 17.4 inches is more likely. And to explain it, if the z-score is closer to 0, means it's more likely to occur. In this case, it's only 0.08 standard deviations away from the mean, as opposed to 1.92 standard deviations away. And if it helps you to think of the visual too, there's your chart. There's X bar, that's the middle. So a z-score of 1.92 would be all the way up here, not many values up there, whereas a z-score of negative 0.08, way more likely to occur. All right, a couple more examples with z-scores and then we're done. These should go quick. Suppose the average battery life of a Duracell AA battery is 21 hours with a standard deviation of 2 hours. It is known that a certain battery has a z-score of negative 1.25. Without calculating the battery life in hours, what does the negative z-score tell us? Well, if it's got a z-score of negative 1.25, where does it fall on this bell curve? Below the mean. The mean was 21 hours. Negative 1.25 is going to be over here somewhere. So you can tell us that if it's got a negative z-score, the battery lasted less than the average battery. In other words, it's below the mean. That's what a negative z-score always tells you. It's below the mean. Now, I wanted to know exactly how many hours it lasted. Remember, a z-score is equal to observed minus the mean divided by the standard deviation. What part of that do I need to solve for? The observed. I want to know what the exact lifespan of that observed battery was. So I'm just solving for a different part of the z-score. Negative 1.25 equals, I'm just going to call it x, because that's what I'm looking for, minus the mean, which is 21, over the standard deviation, which is 2. If we cross multiply, we get negative 1.25 times 2, that's negative 2.5, equals x minus 21. If you add the 21 over, you're going to get that 18.5 is how long the battery lasted. All right, this is obviously a little bit old. Your iPhone 5C lasted for 3 years before it stopped working. Apple claims that phones last 2.2 years on average. If your phone has a z-score of 1.11, what is the standard deviation of iPhone life rounded to the nearest hundredth? So again, if I know the z-score, in this case I know the observed value, and I know the mean, let's find the standard deviation. So this has a z-score of 1.11, so it's above the mean, which is good. The observed value lasted for 3 years. That's the specific one we're looking at. Minus the average, this is the mean, x bar, all over standard deviation. So again, cross multiply, 1.11 times the standard deviation. 3 minus 2.2 would be 0.8. So if I got to solve for standard deviation divided by 1.11, just plug it in. 0.8 divided by 1.11, 0.72 would be the nearest hundredth. So that means on average, most batteries last between 0.72 years away from 2.2. Okay? All right, last one. The brakes on your parents' car lasted that many miles. The z-score is 3.25. That's pretty good. That means it lasted a long time. The standard deviation is 530. What's the average? So this time, again, go back to z-score is observed minus the mean over the standard deviation. The z-score was 3.25. What's the observed? The specific one we're talking about, 62,345, minus the average, I don't know that, x bar, divided by the standard deviation of 530. Okay, so we're going to cross multiply. 3.25 times 530 gets me 1722.5 equals 62,345 minus x bar. If I subtract over the 62,000, so minus 62,345 is negative 60,622.5. That's negative average. So that just tells us that the average is 60,622.5 miles. All right, so that last page is just kind of going through some z-scores and using it to find different information. And before I let you go, I just wanted to start you off on the homework. I mentioned it a little bit during the warm-up, but again, this is kind of from the day 0 notes. So if you didn't watch day 0's video, you need to do that before the homework, or else you won't know how to do this. But if you did watch the video, it's still a little tricky. Number 1 starts with the gas mileage of your car changes from day to day. Depending on the type of car driving you do, here are the data for 25 weeks. You're going to put all of these in L1. So if you did the warm-up with me, go to Stat, Edit, clear everything out of L2, clear everything out of L1. Remember, if you, by mistake, if you do delete instead of clear and it goes away, you can always go second delete, so insert, and then go second 1 to get L1 back and hit enter, and that's how you get it back. But anyways, if you have L1 cleared out, type in all of these. There should be 25 values. So make sure it's 25 values. Double check and make sure you did them right. When you go to do your one variable stats, do the mean and standard deviation, you're going to go to Stat, Calc, one variable stats, but you need to take out the frequency list. There's no frequency chart here. It's just L1. So leave frequency list blank. If you have an old calculator, you can just go Stat, Calc, one variable stats, and hit enter. Don't type anything. Okay. Part A wants you to use a histogram, so you're going to need to turn your stat plot on. So second y equals, you want plot 1 to be on again. And make sure histogram is selected, like I had you do in the day 0 video. And then go zoom 9, and that'll give you the histogram. Okay, so hopefully the rest of these you'll be able to figure out. And then the back is more z-score stuff. All right, so give it a shot, check your answers on the answer key, and let me know if you run into any problems. Good luck.